All right, well, I'm going to get started with some of the housekeeping stuff before we get started. It's a couple minutes after start time. So like I said, if you haven't already, please download the Arduino IDE and whatever adapters you need to connect the USB-A connector in your Arduino to your machine. I'm Matt from a software engineer at ARM, and with us we have Pete Warden, a software engineer from Google, and Fredrik Knutsson, a software engineer from ARM as well. Just a couple of quick notes. We've put audio dial-in numbers if you're having really unstable internet connection or any issues with audio. Please feel free to connect that way. We're recording this presentation. You've probably already been notified of that. We'll hope to have the recording of the entire presentation and workshop up on the DevSummit website within 24 hours. There's a DevSummit etiquette FAQ if you have any questions. And there's a few other people from ARM inside this that we can chat or have a side channel with if you have any issues that you would like to discuss. If for any reason this Zoom meeting ends or fails at some point, just please try the link again. And if for some reason it fails again, give us about 10 minutes and we'll get it restarted. We completely welcome any comments and questions for the speakers. This should be a fairly interactive session. We've got lots of people to help, and please feel free to type within the chat window. And then as we get more interactive in the session, you raise your hand and we can unmute you and have more interactive discussion. So we'll see how this goes. And I'm just going to put up Fred's slide that shows who our speakers are. But then I'm going to hand it over to Pete if we're all ready. All right, I'm going to stop sharing. Pete, take it away.
Awesome. Thanks so much, Matt. So the first thing I'm going to do is actually share a link to my slides in the chat, just so people can follow along, and they don't have to kind of desperately copy down any of the links that come up. So I can paste that in here. And if anybody comes along late, I can maybe we can reshare those that slides link as we go. And also, I probably won't be able to see the chat while I'm presenting in full screen. So if somebody on the ARM side wants to sort of unmute and let me know if there's any, any chat questions or things that come up, that would be super helpful. And with all that preamble, I'm actually going to start sharing my screen and see if we can dive into getting this person detection actually working. So hopefully people can see this. Let me know if not. But what we're going to be doing today is the first half of this workshop is going to be working through a practical end-to-end example showing you how you can use the equipment we've sent you, an Arduino camera and the TensorFlow Lite micro software, to create an image ML application that detects when there's a person in view. So what is this that we're actually putting together? So as I mentioned, we're going to be plugging a camera into our Arduino and then running a machine learning model about once per second to tell when a person is nearby. And to be clear, this, sorry, jump in. Sorry, somebody had a question? Okay. Yeah, feel free to jump in if you, you know, in the chat, and people can unmute you if you do have questions. So this is not doing any kind of recognition. It's not telling you who a particular person is, and it's not even looking for faces. It's just looking for any, you know, parts of the person's body. So it's just trying to tell if somebody is nearby. And the reason that this is a really common application is, you know, if you think about things like TVs or laptops or anything else, there's often you want to be running in some kind of very low power mode, but you want to wake up when there's somebody nearby. So this is actually one of the most common image-based embedded machine learning applications that we run across. And what's nice about this too is that all of this software is open source. So you can retrain the model to recognize things you care about, you know, once you've got this up and running. TensorFlow Lite Micro is very portable across lots of different devices. So you can take the same work that you've done here and actually try it with different devices or different cameras. And like I mentioned, it's a really useful building block to plug into a larger system. For example, to wake up a more power-hungry, sort of maybe a Cortex-A based chip to do further processing. Like maybe when you've detected that there's a person nearby, then you want to do facial recognition or some other kind of, you know, more power-intensive and compute-intensive work. So hopefully you should already have these items that were shipped to you as part of the workshop. So the Arduino device itself, and it should be an Arduino that has these headers, these header pins, an ArduCam mini camera that we're going to connect up, and then 8 of these, let's see if I've got some handy, like at least 8 of these female to female jumper cables, though you may actually have more, and that's fine. It's always nice to have some spares. The things we didn't ship you were, you need a micro USB cable to plug in your laptop to the Arduino to communicate with it. So hopefully you already had one of those. And if you have a laptop with only USB slots like the modern Macs, you'll also need an adapter to connect the micro USB cable. But the good news is that no soldering is required at all. And the other thing I should mention as well when we're getting started is the ArduCam connection has been, we've run into various different issues as we've been trying to set this up. I think for future workshops, we'll be using a different camera model, but we've tried to work through most of the issues. A bunch of us have, you know, have successfully got this working, but there may be some, you know, connection issues that we may not be able to fully debug for all of you in the course of this workshop. So we're going to leave some contact details if you want to sort of keep trying and debug as you dive into this. But fingers crossed, hopefully you should be able to follow along and get this working. So I put the slides in the chat, and I'm going to leave this this slide up for a minute or two, just so you have a chance to copy the short URL down. And to accompany the slides, there's also a document that I put together that has detailed step-by-step instructions on how to get this up and running. So while people have a chance to check the slides, were there any questions in the chat that came up as we were working through this? If not, I'll just carry on.
No questions in the chat. I think most people have just been commenting that they did actually get a cable with their kit.
Oh, awesome. Okay, I don't think. Oh, actually, you're right. I missed it in the bottom of my kit, but yeah, there was a cable. So it's just the USB-C, I guess, that was missing. So if you need an adapter, cool. So I'm going to start by trying to help get the hardware actually assembled. So what you'll need is the equipment that I mentioned before. The trickiest part of this is actually being able to read the silk screen labels on the Arduino and on the ArduCam board itself. One hack that I found really useful, because probably a lot of us don't have either super keen eyesight or a magnifying glass to hand, but you can actually use your phone, use the phone camera to actually zoom in to sort of be a digital magnifying glass if you want to actually look at the labels. And you can see here I've sort of zoomed in with the camera, so you can see the labels that are actually visible on the Arduino, and then the ones on the pin labels on the ArduCam are actually a little bit easier to see. But you can see, especially the Arduino ones, they're pretty small and they can be pretty hard to make out. So I do recommend using some kind of assistance to help you find these. And I'm going to run through this, hopefully not too fast, but I'm not necessarily expecting that you'll be able to wire this up in the time that I'm working through these slides. So what I suggest is that you work on getting the connectors going. I'm going to sort of continue walking through the slides and discussing what needs to, what you actually need to do to get this going. And we'll come back and sort of, answer questions after Fredrik from the CMSIS-NN team has actually given his discussion of, the optimizations that his team has put in to make this example possible. So don't worry if it seems like I'm going too fast. Hopefully you should have the link to the slides, so you can sort of jump back and forth as you're getting these connections set up. So there is a pinout diagram. The thing that you need to watch out for here when you look at the diagram is that it's looking at the Arduino from above, from the side with all the chips on. the connectors are actually on the bottom of the Arduino. So as you're working with this, it will actually be kind of mirrored because it's kind of on the other side. So that's why I find double checking the labels, actually looking at the silkscreen labels on there, to be really helpful. So when you're actually attaching these connectors, make sure you're grounded by sort of touching your laptop or computer case. You take these connectors and you sort of, you'll be peeling off like one at a time. Sometimes there's a little bit of sort of glue that gets stuck, but don't worry about that. And you'll be taking the connector and you should find that with just a very little gentle pressure, it kind of slots into place and should hold reasonably well. And what I find useful is really trying to do one connection at a time. So sort of plug in to the, for example, to the Arduino one end, and then plug the camera into the other end. And it's possible to take them in place once you're done. I actually have not found that necessary. I found the connections seem to work pretty well. So I usually decide not to. And this is the most important table that we have in this presentation. And this is telling you how to connect the pins that are on the ArduCam board up to the pins that are on the Arduino board. And to maybe, if you're more visual, here's a diagram that shows the same thing. So shows where all of the connections actually have to go between the ArduCam and the Arduino. So I'm expecting this will take a few minutes. So like I said, I'm not going to sort of pause too long on this slide. I would recommend that you actually have your copy of the slides up so you can refer back to this and work at your own pace. But again, I just want to stop for a minute or two, let you take a look at this and see if there's any questions that have come up from the chat. And also just have a drink, since it's a bit smoky here in California at the moment, so my throat's a little sore. Okay, so while you're working on wiring this up, I would recommend that you start downloading the Arduino IDE, just because that may take a minute or two depending on your connection. And you can just search for Arduino download, or you can go to this link in the slides. The only thing to watch out for is that the first entry on the page is the web editor. And for these examples, we're actually going to be using the IDE, the desktop application, not the web editor. And that leads us on to the software installation. We have to jump through a few hoops here because there are some patches we actually need to make to the software. This is all still fairly cutting edge work. So there's some things that just don't work totally off the shelf. And one of the things that you need to do to start with is just have your Arduino plugged in using the micro USB cable. And then once you have the Arduino IDE up and running, you'll be installing the software that you need to connect and program that Arduino. And to do that, use the Tools Board Manager entry and search for Embed. And find the, you should see an Arduino NOF 528X boards library to install. So click on that, and that will take a minute or two, again, depending on your connection. But that will give you what you need to be able to connect to your Arduino. One of the most challenging parts of using the Arduino IDE is actually getting the USB driver stack and the USB connection working between your laptop and your Arduino. So when you have your Arduino plugged in, hopefully, once you've installed the board, when you go to Tools Port, you should see a port that has the name of the board, Arduino Nano 33BLE, in brackets next to it. If you don't see that next to any of the ports, there might be a connection issue. So the first thing to do, if it seems like it's not showing up, is unplug the USB connection from your laptop side and plug it back in, and then go back to the Tools Port menu and see if it's shown up. If that still isn't showing up, there may be a USB UART serial driver issue on your platform, which is hard to debug. We have some troubleshooting tips towards the end, but it's one of the most painful parts of getting the Arduino stuff up and running. And one initial sanity check to try is, once things seem to be working, once you do have a port connected, go to Tools, Get Board Info in the menus, and you should see kind of a small pop-up with information, including the BN field, which should tell you that it's an Arduino Nano 33BLE. And just because there are often issues with connecting and uploading to the Arduino board, I recommend that you actually, before you even get into the machine learning side, just try and use one of the more simple examples just to make sure that you can upload and program the board successfully. So in the Arduino IDE, if you go to File, Examples, 0.1 Basics, and then choose Blink, you'll see a sketch window show up. In that sketch window, if you press the Upload button, it should compile and then flash the script onto the Arduino. And if the connection is all working fine, it should just build and upload. And you should see an LED blinking where it's on for 1 second and then off for 1 second. So if that all works, then congratulations, you've actually got a successful Arduino IDE connection up and running. As I mentioned, this is cutting edge stuff. Not all of the code works straight out of the box for some of the libraries that we're using. So I recommend that you have a code editor installed on your machine if you don't already. I mean, it can be as simple as TextEdit or Notepad or something like Emacs. I just put in a little dig at VI here just because, VI, because I keep getting stuck in it. Yes. But you can use VI if you're so inclined. The simplest one that I recommend if you don't have a strong preference is actually VS Code, because it's nice and cross-platform, and it's all in all very nice. One thing you need to do, most of the libraries that we're using, you can actually get from the Arduino IDE library manager, but the ArduCam library isn't present there, so you'll need to grab it from GitHub, and I have a link to the actual version that I grabbed when I was testing this, so you can grab that from the slides. You'll then, once you've unpacked that zip, you'll need to copy the ArduCam folder that's inside there into the place where your Arduino libraries live. And this is different depending on whether you're on Linux, Mac OS, or Windows, but it's usually somewhere in your home directory, documents, Arduino, libraries, and you should already find a folder there, and so it should just be a matter of like copying that ArduCam into that libraries folder, and you may have to close and open the IDE. It seems like I didn't have to on Mac OS, but maybe I did on Windows. But once you've done, once that has worked successfully, you should see ArduCam show up in the file examples menu in the Arduino IDE. So that's a sign that the library is being successfully loaded. Now we're actually going to have to do a little bit of modifications to the ArduCam library so that we can actually use it. You'll have to open inside that same libraries ArduCam memory saver, in that Arduino libraries ArduCam folder that you've just copied to, open up the memorysaver.h file, and you'll see a bunch of hash defines for different camera models. So just make sure that the OV2640 Mini 2MP is undefined, and all of the others are commented out, as you can see here, and then save the file out. Next, we'll actually use the Arduino library manager to install TensorFlow Lite, which is the code I work on, which does the actual machine learning part of all this. So there you should just be able to look for Arduino_TensorFlow Lite and install the latest version. You're also going to need to install Jpeg decoder so that we can take the JPEGs that we're actually getting from the ArduCam and turn them into the pixels that we need, the arrays of pixels that we need to feed into the machine learning model. And again, this one you can actually grab from the Arduino library manager using Sketch, include library, manage libraries, and then doing a search for JPEG decoder and grabbing the latest version. This is another library that we actually need to patch. So actually, somebody pointed out an error in this. It should actually be user_config. But you need to open this file, again, from the libraries folder, and make sure in user_config.h that both load SD library and load SD fat library are commented out, and then save the file from your editor. The reason for this is that by default, Jpeg Decoder assumes that you're going to be saving out to an SD card of some form, and that means a dependency on some kind of SD card library. Because we're not going to be saving this out, we're just going to be passing it to machine learning. We don't want to include that dependency. So, as I mentioned, there's likely to be some head scratching as you're working through this. There's a lot of steps. One of the things that is very common is that if you see weird compile errors, once we get to the TensorFlow sketch in a few slides, you have to make sure that the board is actually selected in the Arduino IDE. Make sure that it says Arduino Nano Sense BLE33 it's usually in the bottom right corner, I think, of the IDE as you're getting things up and running. If you're seeing ArduCam API errors, once we try and run the example, the first thing to check is just go through and make sure that all of your pin connections are exactly right, because that's an easy way to run into problems. We've also had some reports that sometimes the ArduCam doesn't seem to be getting enough power, and we have some potential ideas on debugging that, but it might be outside the scope of the time we have in this workshop. The upload and monitor system can sometimes display errors as you're kind of uploading your code. Just make sure, sometimes the port seems to get forgotten. Just make sure you go to the tools sort of port selection again and make sure the port that you want is correctly selected. So how do we actually get the example that we want running? Now that you've installed the TensorFlow Lite library in Arduino, you should be able to go to File, Examples, Arduino TensorFlow Lite, and choose the Person Detection Experimental. This is going to change to just be plain old person detection in upcoming versions of the Arduino library. So I've just made a note for anybody who's sort of coming back to this in the future when the library might have changed, that if there's no person detection _ experimental, you can just use the person _ detection version instead. But if you do see person _ detection _ experimental, use that. So I hope that makes sense. In the sketch, if you go to the Arduino image provider.cpp file, you may have to go to the down arrow that's on the left to see, because there's quite a few files in the sketch. You'll just need to comment out a few lines that are checking for a particular camera. Use the Arduino IDE, not the code editor, to do this, and then you won't have to save out the file. You can actually just hit the upload button after making these changes, and then you won't actually have to save anything out. Once you've done that, you should be able to press the upload button in the top left corner, and if you can, open the serial monitor terminal once the upload is completed, and once all that is done, let me just see if I can plug in my device so I can actually show you. Just hold. If you can see, drag this into position. If you can see, this is my completed version. So hopefully you should be seeing a red light when I have the camera pointed at the screen. And then when I point the camera at myself, I think it looks like it's actually turning green. So red when I've got the camera pointed away, and then green when I've actually got it pointed at myself. You should also see scores showing up in the terminal window, and high scores means for a person means that the model has a pretty good confidence that there's a person in view. And this should all be running about 1 frame per second, thanks to Fredrik and his team's hard work. It used to be taking several seconds to actually complete. So he's managed to speed this all up multiple times, which makes it a lot more usable. And that should be, that should be hopefully an end-to-end demo. So once you've made it that far, you might be interested in doing more. A good place to start is the TensorFlow.org hub that actually has a lot of information on using TF Lite Micro. Me and Dan, who I think is on the call, have put together a tinyML O'Reilly book, which you can check out and get some free chapters at tinymlbook.com. There's some great talks you can actually find at tinyml.org. And I also would like to give a shout out to Dan's startup, Edge Impulse, who have built a great ecosystem around a lot of this tinyML work. And in particular, if you want to train a model to detect different things, we actually have some, code in our example repo for that as well. So as I mentioned, I'm sure there's going to be lots of head scratching and debugging because this is all pretty new and cutting edge stuff. So my email is petewarden@google.com. And you can also follow my adventures on Twitter at Pete Warden. And with all that, I'm going to throw the floor open to some questions before we jump into Fredrik's discussion of how he and his team managed to optimize the code that you're using.
Yeah, well, I see one question in the text about yes, this will be recorded and sent out within 24 hours or about 24 hours from when we started. And if anybody has any questions now in the chat, or we can unmute you if there's any more sophisticated discussion to be had, just please let us know in the chat right now and we can unmute you. Let's see.
If not, I can just hand over to Fredrik.
Thanks, Pete. That's a great walkthrough. Can you hear me?
Yes. No, thanks, Fredrik. I was just unsharing.
Yep, great walkthrough. And I really like this demo because it shows us that you can do some great machine learning applications on really small and power efficient processors that exist on the market today. And so it kind of gives you an indication of what we can do today and gives you a hint maybe on what we can do in the future on even more ML capable hardware. So this Arduino Nano 33, thank you, is powered by an ARM Cortex M4, and like Pete mentions, it utilizes CMSIS-NN in order to do the inference faster. So while you continue wiring up and installing and getting it up and running, I will talk about CMSIS-NN. And I think we can skip 3 slides forward. There we go. All right. So first question, what is CMSIS-NN? And if I take one step back and talk about CMSIS, CMSIS stands for Cortex Microcontroller Software Interface Standard, and it's a collection of API, libraries, debug, utilities, etc. And it's intended to make your life as an end user simpler by accelerating and simplify creation of microcontroller applications. There are components such as an RTOS or optimized DSP libraries, optimized neural network libraries. And this is all open source software. So it comes with an Apache 2.0 license, so it's a permissive license, so it makes it quite easy to use and build upon. And CMSIS-NN stands for CMSIS for neural networks, and it provides you optimized kernels for our Cortex-M processors. And I've added TensorFlow Lite for microcontrollers in here because this is our entry point to using CMSIS-NN. And I will talk more about how it is integrated and how it utilizes all the features of TensorFlow Lite Micro. I can also mention that there are 2 main categories of optimizations, and that is our processors which has DSP extensions, and our processors that has MBE enabled devices, such as the new Cortex M55. All right, next slide, please. So first, let me just mention briefly the Cortex-M processors. So in the highly embedded market, we have ARM offers a range of processors, and those are called Cortex-M. And they are the smallest and least power hungry of all processors. Cortex-A, Cortex-R are for the more or less embedded side of the market. So if we focus on the Cortex-M spectrum, we have on one side Cortex-M0, which is the smallest and lowest power consumer of all the processors. And if we move a little bit towards the middle of the spectrum, we have the Cortex-M7, which is the most capable when it comes to running control code or regular code. And I think sometime next year we will have we will see a Cortex-M55 in the market, and that is a processor that has or offers you the highest ML performance out of all these M-class CPUs, and it does so utilizing helium technology. We'll talk more about that in a couple of slides. And as you can see in the green, one slide back. It's interesting to mention that it's up till this date, more than 52 billion Cortex-M have been shipped. So it's an impressive number. Next slide, please. Okay. So we talked about CMSIS-NN and what that is, and that it provides optimized kernel implementation for neural networks for Cortex-Ms. So now I'll talk about what kernels are optimized. And our strategy is to optimize where it matters. So I'm going to mention a couple of things about that. I'll start off with quantization. So we focused, or I'll take one step back. In the embedded domain, usually you have quite tough memory constraints, power constraints, and cycle constraints. So 32-bit data, 32-bit float may not be ideal for this segment, but 8-bit more suitable due to the memory constraints. And we've focused on the int8 per channel symmetric quantized data. You can see the relation between the real world value and the quantized value in the formula below. Now, TensorFlow Lite Micro supports asymmetric uint quantized data as well, but new tooling, new reference kernels, and so on will focus on more on int8 data. And so I want to mention that because it sometimes can cause a little bit of confusion. All right, then operators. The majority, or as you can see on the right-hand side, we have 4 pie charts. These are a couple of, or 4 representative networks out in the wild, representing speech recognition, face recognition, human activity recognition, and image classification. Now, if you look at the total amount of compute in these kernels, you will see that the majority of the compute ends up in only a handful of operators. So from the pie charts, you can see that the conm 2D depthwise conn fully connected and to some extent max pool takes some significant amount of compute. So this is the kernels, this is the operators that we focused our optimization effort into. But we're always interested in hearing about new use cases and new ops, new networks that where you can see a need to optimize one of the kernels that we do not support today. So if you spotted any such network, please do open a ticket on our GitHub repository for CMSIS. Okay. Next slide, please. Okay. Now, CMSIS-NN involves a few different optimization techniques, but I will focus in this slide on the most significant optimization, that is the use of SIMD instructions. SIMD stands for single instruction on multiple data. Now, one such operation is a MAC, multiply and accumulate. And neural networks just happen to have a lot of MACs. So what it means is that you can basically do a multiply and accumulate in one cycle, or even multiple MACs in one cycle. And there's 2 categories of CMD support: DSP extensions, and like I mentioned before, the M-profile vector extensions, also known as helium technology. So if we start with the DSP extensions, two examples of processors that are capable of that has the DSP extension is M4 and M7. M4 can do 1 MAC per cycle. M7, due to its dual issue pipeline, can do 2 MACs per cycle. Now, if we look at the Cortex M55, which I mentioned before, it can do up to 8 MACs per cycle. And it does so utilizing the MB, M-profile vector extension, or helium technology. And how that works, I've attempted to illustrate this in this slide. So basically, you have, I've written an equation down. It's the one that we want to evaluate or compute. So we have 16A, 16Bs that we want to multiply and accumulate. And how that is done is you take all the A values, the A vector, 8 bits per number, you put that in the 128-bit vector register. So it's the vector registers that is the core of these helium technology. And you do the vice versa for the B vector, and then you execute one of these SIMD instruction on this data, and you accumulate it into a resulting vector or register Y. So 16 multiply and accumulate in 2 cycles. So that's where we get the 8 MACs per cycle. Let me stop there and see if there are any questions so far.
The chat is clear.
Great. Then we can go to the next slide, please. All right, so we know what CMSIS-NN is, optimization for Cortex M's. We've seen some part of the optimization techniques that have been used. And as you could see from the demo, if you get it up and running, it takes about a second now to do the inference, a little more than a second. And like Pete mentioned, it without the optimization, it would take several seconds to do the inference. In these slides, we show the performance improvements of an M55 on a couple of popular networks, MobileNet V2 and Web2Letter. And as you can see, we get about 10 to 11 times performance uplift on these 2 networks. Now, the performance uplift depends on a lot of factors. You can have a different compiler optimization level. You can have different memory access latency and whether you have a cache or not. So this is ballpark numbers, but it gives you an idea on what you will get by using CMSIS-NN. And I want to emphasize as well that CMSIS is open source software with a permissive license, so it's easy to use. So you get this basically for free. It doesn't cost you more power or anything. We just utilize the CPU in a better way. I saw some question there on the feed. Should I take that?
Yeah, mostly question about the Arduino installation.
Okay.
I have a general question on this. Are you able to hear me on the conference?
A little bit low, but
okay. The question was on the helium technology. Does that require the the bits to be arranged in a certain registers to make sure the performance can be achieved? If so, is there any provided software or APIs that can help an end user?
Yeah, so it requires this the bits to be arranged in a certain way, but this is what the CMSIS library does for you. It will basically have well, a little bit simplified, an API for the convolution, for example, where you provide a pointer to the filter data, pointer to your data, and then it will calculate it, and it should be bit exact to the calculations done by the reference kernels in TensorFlow Lite Micro.
Thank you. So the performance depends on how that API is used by the end user. Right? So is there any generic higher level recommendations or software example flows that will say how to best use the CMSIS APIs to get some of these benefits?
It's a good question, and we will come to that in the next slide. So this is where TensorFlow Lite Micro comes in. It's a simple build switch, as we will see in some of the upcoming slides. Let me get to those, and then we can get back to the question if
Sure.
if there was some uncertainties. All right. Any
We have
more
also
questions?
another question. Tara asked if with the various, Ram asked if similar to TensorFlow package for Arduino, are you planning TensorFlow pack for Kyle IDE?
I was just typing a response.
Okay.
Yeah, we are working on that. We're pretty close. We have that working internally and expect to have some announcements probably in the next month or so.
Great. Okay. Can you go to the next slide, please? All right. So how to utilize these CMSIS-NN kernels? CMSIS-NN has an API, which is called from the TensorFlow Lite Micro operator. You can find the glue code highlighted in yellow in this slide. So in this folder, you will find some C functions that actually make the call into CMSIS-NN. And how do you enable these kernels? That is done by using a mechanism in the TensorFlow Lite Micro build system called tags. So you basically set tags equal to CMSIS-NN, and that will dispatch the compute to CMSIS-NN kernel where they are available, and use reference kernels if there are no optimized CMSIS-NN kernels available. And this, I would say, put dispatch in quotation marks, because this happens compile time. So it's not like you compile in both the reference kernel and the optimized kernel in your final binary. You only compile in either or. Did that answer your question from earlier on?
Yes, but can you repeat what's the difference between the reference kernel and CMSIS-NN kernel? Are they two separate kernels doing the same thing, or are they augmenting each other?
It's the thing with the CMSIS-NN kernels is that they in CMSIS-NN we do these we utilize these SIMD instructions in order to do multiple max in one cycle. The reference kernels are more pure C, whereas the CMSIS-NN kernels utilize processor intrinsics such as the SIMD.
Okay. So at compile time, there's an option for us to pick CMSIS-NN as you showed on the screen.
Yeah, yeah,
okay.
Exactly. Any more questions?
So I see a question on the chat which asks, does it mean we can drop the reference kernel? Because if CMSIS is the most optimized, why do we need the reference kernel then?
Well, one use case is if it's not an ARM. That would be one use case. But I think in general it's good to have a reference as well. We optimize our CMSIS kernel in order to make sure that they are a bit exact to the reference kernels.
There was also another question in the chat. The 10 times and 11 times improvement, it is with reference to which base platform?
Okay, sorry, I was unclear there. So it's reference kernels performance, pure C performance versus the CMSIS-NN optimized kernels on an M55. So that's the comparison, reference versus CMSIS-NN kernels. And the system we used was is a reference system that we put a bit file that we put on an FPGA. But we ran the same hardware for both tests, so it's that was the comparison. That's good. We get a lot of questions. Any more? Okay.
So I've got another one coming in. So the performance enhancement makes use of SIMD native instructions and bypasses C compiled counterparts.
Yes, in one way, and no in another way. I think I would have to defer that question to one of the team members, because it's it requires maybe some drawing to elaborate on that. But please drop me an email, and I will put you in contact with one of the guys in my team, and he can elaborate on that.
Okay, and then one of the other questions is, what would be the improvement on an M7?
On an M7, sorry, I can't give a number straight away on one of these networks, but so we I'll have to look into what numbers we have on that, so I can't answer. Sorry. But since M55 is a dedicated, is really good at doing machine learning workloads, of course we will see a little bit more gain in the M55 as compared to M7, despite its dual issue pipeline.
I think that's all the questions for now.
Right, thank you. Thank you, Rob. Can go to the next slide, please. Okay, so here is an example. If you want to do what you're doing right now, but even more from scratch. So in these 4 steps, step 1, 2, and 3 is optional. This is already, the Arduino IDE has already integrated TensorFlow Lite Micro with CMSIS-NN optimizations into their latest version of the TFLu library. So 1, 2, and 3 is optional, but I want to show this to emphasize that it's not 15 steps to accomplish this. It's quite a few steps. So first, what you have to do is you clone TensorFlow repo. Then you write this make line. I've highlighted the tags equal to CMSIS-NN, which means that the build system will remove the reference kernels and put in the optimized kernels into the final binary, or in this case into the generated Arduino project. And then you basically unzip the result that you get into your Arduino library. And now this is only one example. Like Matthew mentioned, we're going to be able to do the same thing for Kyle. You can do the same thing for Mbed, or you can generate a more bare metal binary without any overlying framework. And you can see instructions on that in the TensorFlow Lite micro repo. I have a link in the next slide, I believe. So if there are no further questions, there we go. So in the first link, which is in the TensorFlow Lite repo, you can find a README with instructions on how to generate CMSIS-NN optimized embed projects, or like I mentioned, more bare metal without any overlying framework. So that's the first link. The second link is to our GitHub repository for CMSIS-NN. And the last link is more details on the CMSIS-NN kernels that we support for the different CPU architectures. And that's all the slides that I had. How is the wiring and the installation going out there? Any more questions in the feed?
Maybe it's a dumb question, but can you know the difference with C compiler and CMSIS? Can we view CMSIS like an enhanced C compiler, or
no?
How do you explain?
It is so in essence, if you open up the kernel and look at it, it's basically C code as well, mixed up with some assembly, some utilizing SIMD intrinsics. It kind of it uses different techniques to nudge the compiler into using more optimal intrinsic instructions. So it is a set of C functions, but they're just more optimized in order to run as good as they can on our processors.
Thank you.
And for those asking for links to the video and slides, those will be posted over the next day. And you should, if you're signed up for the conference, should get a link via email when we do that.
All right, that's all I had. See if we find more questions.
Okay, since we had time, maybe extend the earlier question on the C compiler versus CMSIS. So is it right to think that we can have an ARM code compiled with just the C compiler without using any CMSIS, or is CMSIS always required for working on top of ARM hardware?
As when it comes to CMSIS-NN, we can make general C code. In general C code, you can will work for any type of data structure, any type of memory layout. What we do in CMSIS-NN is kind of nudging the compiler into using intrinsics, writing intrinsics by making some certain assumptions on them. So it's more like a hand-coded, more optimal way of writing C. Of course, we have compilers support that can directly dispatch certain functionality, but not as optimal as CMSIS-NN is doing for machine learning workloads.
And if I were to extend for any other CMSIS, not specific to CMSIS-NN, so assuming this response is applicable for other CMSIS as well?
I don't know, actually. CMSIS DSP has utilizes the same SIMD instructions and intrinsics in a similar way to CMSIS-NN. For example, for FFTs and other types of mathematical DSP workloads. But so I guess in that sense, but then CMSIS is much wider than that. It has components for debug help and consistent peripheral access and RTOS and so on. So I can't answer really for those other components.
Thank you.
Welcome.
So we have some other question in chat. Chuck B asked if, so it makes sense that Mac will be a logical place to optimize ML with native instruction where you can do multiple ops into one cycle. But was this an intuitive guess, or did your profile code to see this hotspot?
No, it was intuitive since the convolutions is basically consist of multiply and accumulate. It was a quite natural first choice, but then of course CMSIS-NN consists of a lot of other optimization. I chose to focus on the main contributor to the performance uplift, and that's the SIMD instruction with max.
Cool. Another question is, does M55 have a dedicated NPU?
No. It has the vector registers and it can do the simultaneous mathematical operations. But we have something called the Ethos U55, which is a dedicated U, which you can pair up with an Cortex M55.
Thank you.
And that's also coming out sometime next year on the market. It's good questions. Any more?
So I wondered if you looked into just optimizing the neural networks with just binary operations instead of just 8 bits. So only like binary flips. Does that make sense?
Yep.
Yeah,
totally. It's a good question. I've only seen the 1-bit neural networks in a presentation or so, but I know smaller data types than 8 have been discussed in many different contexts. For example, like an int4 or so, but we don't have any optimization in CMSIS for that.
But do you see that there could be some benefits doing vectorized operations on such small integers or numbers?
I'm assuming there would be some quite useful operation on those small data types. But it's since it's smaller than 8-bit, it may be a non-standard data type, which may make it slightly difficult, but it definitely makes sense in the ML use cases.
Yeah, thanks for your answer.
Thank you.
All right, multitasking on the chat here. It looks like a few people have gotten the example running, which is great. And a few people were asking about compile times, and yeah, that it's going to vary on your host machine, but a few minutes is not abnormal. Yeah. I don't see, I may have missed a few questions, but Cisco, thanks for covering those. If you have any others, now is a great time to get really interactive and unmute yourselves. All right, I guess if there are no further questions, we can start wrap up. This one's maybe good for Pete if you're still there. How is it to, or how easy is it to retrain this model?
So it takes a few hours, but I'll link to the instructions. The instructions are in the tinyML book that me and Dan published, but they're also just open source. Let me see if I can find a link, and I'll put it in the chat. So there's a link to how to train the person's detection model. There's a question that Dan might be able to help with about edge impulse, since I mentioned that, if Dan is around.
Hey, so yeah, these are two questions that go well together. Thanks, Pete. So I think what we do with edge impulses is essentially, if you think about this whole flow from collecting data, analyzing the data to make sure that it makes sense to train a model with, it's going to be possible to train a model with, figuring out the architecture for your model and sort of how it looks architecturally, what all the hyperparameters are, how everything needs to be configured, and even whether you need to do any signal processing. So for vision, you'd usually not do a huge amount of signal processing, but for things like audio, you might want to do some pretty intense stuff to convert a raw audio signal into something that the neural network can more easily understand. So that's a whole bunch of work. You've then got, once you've trained a model, you need to be able to evaluate it and test it and see that it works well on a test data set, test it out with real world data, test it out with devices that are connected in the field. And then once it comes to deploying a model, there are all sorts of different devices, some of which support extensions like CMSIS-NN, some of which don't, all which have these sort of varying support for varying types of accelerators for signal processing or for running neural networks. So the whole world of deep learning and running deep learning on embedded devices is super complicated. TensorFlow Lite for microcontrollers is a really kind of core part of this flow. at least one approach to this flow. CMSIS-NN is also a core part of that, but platforms like Edge Impulse are basically giving you this kind of high level view of end to end. What are all the different ducks that you need to get in a row in order to produce a successful application that's deployed to a device? And so what we try to do with Edge Impulse is to provide tools for every step along that flow, and then for working with your team on top of that. So there are a number of similar platforms as well. I don't want to just kind of like toot our own horn here. There are a few different approaches people are taking to this, but I think like beyond the core technologies, the core runtimes and kernels that things like TF Lite for microcontrollers and CMSIS-NN provide, there is a lot of other work that goes into building an embedded ML project from a developer point of view. And especially when you start thinking about targeting all sorts of different devices that have all sorts of different special accelerators and compilers. So that was a long rambling answer, but to tie that in with the previous thing, so training a model like a vision model, for example, that involves collecting a bunch of data, evaluating the data to make sure it's nice and clean and makes sense, and then finding the right model architecture to train with that, and creating a model and then evaluating it afterwards. And if you look at the instructions that Pete posted in the chat here, you can see there's sort of a hands-on low-level way to do that, where you're kind of going through all the steps yourself. But for most engineers, if you're an embedded engineer and you want to focus on the thing that you know about, which is embedded development in your kind of problem domain, that stuff's a bit of a distraction. And so hopefully platforms can help take away some of the like needing to learn Python, for example, and mean that you can just focus on the part that you're highly skilled at and use a tool for the rest of it. So Edge Impulse can spit out a model that you can use with TensorFlow Lite for microcontrollers. It can also build you a C++ library that uses TensorFlow Lite and CMSIS-NN that you can just drop into your project. So all the unpleasant, difficult, tedious glue stuff we take care of, as well as some of the user experience.
Great. Thank you for that, Dan. We have a few questions about compile errors. It looked, yeah, I saw a few comments go by that people had successfully compiled, and I did as well while we were doing all this. Without more specifics on what people are running into, it's kind of hard to answer. I hope those that aren't successful can reach out to me or others that have shared their contact information, and we can try and help you with more specifics. Also within the Arduino forums, we may be able to have some discussion. So yeah, sorry, this is not the best format for addressing individual compile errors. Let's see. Yeah, people are still getting wiring done. Yeah, I think we've all, or a few of us, have shared contact information, so we're willing to follow up as you guys finish getting things wired and getting things going. And I should also say, tomorrow Pete's going to have an office hours. So if you haven't signed up for that already, I don't know if I should have checked before. I think we're going to be doing 20-minute slots with small groups. So and I will be helping host that. So Pete and I will both be there. So this isn't your last chance to ask questions of us.
Yeah, I should also call out there's another workshop with Kwabena from OpenMV, which is going to be using TensorFlow Lite for vision stuff. So that will involve training your own model with Edge Impulse, and it all uses TensorFlow Lite under the hood. So that's worth checking out too.
Great.
And that's tomorrow. I don't know if I mentioned that.
People having trouble uploading the sketch. We've run into all sorts of different interesting things with adapters, whether they're powered hubs or not, and hitting the reset button doesn't necessarily put it in a graceful reset mode. Sometimes you have to do a full hard power cycle on the Arduino, just disconnect it completely. And I apologize if I've missed any questions. I'm scrolling back through. Yeah, if there's anything we've missed, please reach out to us. It seems like we've covered all the questions. And if you have any last ones, please feel free to unmute yourself now and ask. Otherwise, we will wrap up here, and looking forward to hearing. Oh, okay. And the questions about, those for those that have arrived a little bit late. Dan and Fredrik have both posted their email addresses. Pete again, and I'll put mine in a sec. For those who arrived late, we will have the session uploaded in about 24 hours, the whole video, and the slides as well. And obviously Pete's already shared his slides, so that link is in there in the chat a whole bunch of times. All right, and here's mine. All right, I want to thank you, or thank all of our presenters and all the people who have been helping answer questions, and thanks for all the good feedback. We look forward to seeing what you guys do with these boards or other examples in the TensorFlow Lite micro for microcontrollers. And great. I'll go ahead and end this now, but please be in touch. Thank you. Thanks all.
Thanks everyone.
Thanks everyone.
Thank you.
Bye.